Good evening, and welcome again to Public Perspective. I'm your host, Kevin McDermott. And although sometimes we've been accused of spacing out on this show, tonight we're actually going to go into deep space because our guest tonight, Nichols from the Adler Planetarium, an astronomer. We're going to talk about outer space.
Absolutely. My favorite topic.
Well, Michelle, welcome to the show. So
Thank
good of
you
you
so
to be
much.
here.
Thank you.
So let's start with something really, really fundamental. What is astronomy?
Astronomy is the science of everything in the universe, essentially. How it works, what's out there. And it's a topic that has been near and dear to my heart for pretty much my entire life.
And near and dear to the hearts of most humans since before recorded history, I think.
Pretty much, yes. There are suggestions that humans have been making pictures in the stars for thousands of years, if not even longer than that. And just connecting to the sky. It's a little harder these days sometimes because of the amount of lights in our sky, but we're working on that.
Well, we have satellites in outer space now, right?
Absolutely,
so,
yes.
So we can see outside of the atmosphere.
Absolutely. We can look down at Earth. We can look out into space.
So what got you interested? You said as long as you can remember, you've been interested in the stars.
Yes.
So why?
Well, when I would be asked this question, even a year ago, I had a stock answer. I had my answer down pretty well. But then I was thinking about it relatively recently, and I figured out when I was about 4, Star Wars came out.
Yeah.
And I still remember seeing it in the movie theater. And it's actually one of my earliest memories. I remember when the Death Star blew up, everybody cheered.
Right.
And then just a couple years later, the first Star Trek movie came out. My mom got me kind of into Star Trek, so that was cool. And then,
there's a competition between those two fandoms,
true.
right?
I don't,
Okay,
I don't
Those are religious wars. We don't get involved.
Yeah, no, we don't talk about that. No, I cross both lines.
Okay.
I can straddle both worlds. But what I used to say as the start of all that was, my interest in astronomy was Carl Sagan's Cosmos TV series. It came out when I was 7, almost 8. But what I realized relatively recently was my interest at least started a few years prior to that. At least went, oh gosh, there's this stuff out there. It looks really cool. They do cool things. Things blow up. It's really neat.
Supernovas, in fact, some of the largest explosions in the universe.
Exactly. And so once my parents realized I was interested in that, we became members of the Adler Planetarium. So we used to visit when I was a kid for several years. And things just sort of snowballed after that. I had a subscription to Astronomy magazine. I went to space camp for a couple of years, worked at space camp for a couple summers, volunteered at a planetarium.
Making you officially a space cadet.
Exactly.
Right.
Thank you very much.
And I'm sure that's the first time you've ever heard that joke?
No. No, actually, the one that I hear most often is people ask me, wait, Michelle Nichols, did you know that there's a character, there's a lady on Star Trek? Were you named after? No, as far as I know, no, I was not. My parents needed an M name, so.
And there's a difference of one letter, by the way.
There's a difference in one letter. I would love to be associated with her in any way, shape, or form. She's pretty cool, so.
And she was a forebearer of many female roles on TV. She was one of the first.
Very much, yes.
Really a pioneer.
She was a groundbreaker, and what I learned relatively recently was she was initially, I think after the first season, thinking about walking away from the TV show. And who got her to come back? None other than Dr. Martin Luther King, who was a fan of the show and told her that he was a fan. He and his family, it was pretty much the only show that the whole family could watch together. And so she thought about it. She went, oh, okay, yeah. I think
she was portraying
stick around.
Not just someone of color, but a woman of color.
Absolutely, and a woman of power.
Yes, responsibility and capability.
Yep, 4th in power, I think, after the captain and Mr. Spock. And
you're exceeding my fandom level of knowledge here. So.
Well, I must say, I sound like I know an awful lot, but I need to thank one resource for this. It was the Stuff You Should Know podcast.
Okay.
They did a episode recently about her.
Star Trek and
about Star Trek,
about Uhura.
Yep.
Gotcha. So we know a little bit now about you being essentially a Trekkie and a Star Wars fan. heavy into the geekdom part of the universe and realized that there's really something substantial behind all this, right?
Yeah, yeah. And the fact that it is knowable, that's the amazing part to me.
Well, now, if I can interrupt for just a second, what I find most fascinating about science generally, but astronomy in particular, is what is unknowable, the limits of knowledge, which I think we see all the time in the study of the cosmos and cosmology in particular.
The way I like to think about it is we are here on Earth. The only other place humans have been is the moon. Our spacecraft have been out in the solar system. We've got a couple that are outside the solar system. And the only way we have of knowing just about everything in the universe is the light that comes to us. And how much we've been able to figure out is pretty astonishing. And the reason that I like to take it that way is sometimes when I take a telescope out and have people take a look through and look it up, and go, wow, that's really cool. How far away is that? Or what is that thing? Or whatever it is. And I'll kind of give them a sense of how far away the object is. The light from, when you're looking at Mars, the light took 5 minutes to get here, or 20 minutes to get here, depending on where it is.
Right.
And you go, oh, that's kind of far. And then you start to think about how vast the universe really is. Or I show you a fuzzy thing through the telescope, and I go, yeah, you see the light that left it during the Roman Empire. And then you really go, wow, that is far. Oh my goodness, I'm small.
And so we're also looking back into history when we do that.
Yeah, you're looking back in time.
That light reflects a state that happened during the Roman Empire. So whatever's happening there now, we have no way of knowing that,
right.
or at least not currently.
Not currently. So the object in question is something that I was showing people through our big observatory telescope at Adler last Friday. We were looking at the Orion Nebula. Just to explain it, a nebula just means fuzzy thing. And it's the Latin
That's
word.
the scientific term?
Well, it's the Latin word for cloud. And basically when early astronomers saw these things through their telescopes, they didn't know what they were. They all looked fuzzy. And so they gave them the Latin name for cloud, because they just all looked fuzzy. Then they started saying, oh, this looks like a spiral nebula. This looks like some other kind of nebula, planetary nebula, which has nothing to do with planets. The problem in astronomy is we never throw names away. And so as you know more about these things, then you realize what they are. Well, the name still sticks. But the Orion Nebula, the light comes to us from about 1,400 or so light years away, meaning it took that long, that many years for the light to get here. And so to know what that thing looks like tonight, or last Friday when I had the telescope out, we have to wait another 1,400 years.
So you and I, won't ever know that.
No, we will
unless
never know
we
it.
are reincarnated, which is another question altogether. Right?
Different show.
Different show, yes. So you mentioned we know the outside universe through the light that comes to us, but before the show we were just talking about recent advances in science, what scientists now refer to as our ears, the LIGO Observatory, which measures gravity waves that were long predicted by Einstein, and were never discovered until just recently, which is within the past year, right?
A few years,
and a half,
yeah. Yep.
And so this is a different way. This is a different way to know the universe, right? Light is radiation on the spectrum of all possible forms of radiation. But gravity waves are not radiation. They're something else.
Gravitational waves are essentially ripples in space-time. So
and space-time is the fabric of the universe.
Fabric
right?
of the universe. Think of it as, we've got a carpet here on the floor. If you lift up that carpet off the floor, stretch it out, maybe put a bowling ball in the middle of that carpet, or a rubber sheet, or whatever you've got. Put a bowling ball in the middle of that. It's going to stretch that rubber sheet out. Put an even bigger object into that rubber sheet. It's going to stretch it out even more. Put a black hole in there. It's essentially going to be something that, as long as if you get close enough to it, you're not going to escape from it. But the mass of the object determines the warp of space. So Earth has a smaller warp than the Sun. The Sun has a smaller warp than a much larger star, and so on.
And this has nothing to do with warp drive, by the way. We should tell our audience. Totally different subject.
Well,
Well, you never know.
Kind of. Warp drive is you're essentially wrapping space around your spacecraft, I think, and that's where my
folding
knowledge.
space.
That's where my knowledge gets a little fuzzy. But
Again, the
like a
limits
nebula.
of our fandom knowledge.
Yeah,
have been
exactly.
reached,
So,
right?
but the
So the warp of space.
the warp of
different.
space, yeah, it's different. Basically when you've got two objects that are massive, like black holes, and they each have their own warp, they will collide, they will rotate around each other, and then eventually merge and collide. Some of the energy of that collision is converted into these ripples of space-time, which then go out, kind of like when you drop a stone in a pond. Then you've got the ripples that go out. Actually, that's probably not a bad way of thinking about it. If you are over on that side of the pond and I'm on this side of the pond and you can't see me, I drop a rock into the pond, the ripples will go out. You may not see the rock, you may not see me, you may not see anything, but you can detect those ripples and you know, oh, somebody was there. Something happened, and it was somewhere out there, maybe that way. If there were two of you, two detectors, you could go, oh, it's that way. If you have three detectors or more, you can probably pinpoint where that object did its thing a lot more precisely.
And in our case, LIGO, the observatory that captures these gravity waves, there are two of them.
There are two of them, and there's another one, I believe, that has come online or will very soon in Italy called Virgo. And then I think there is, I believe it's in Italy. Don't totally quote me on that. I think there's another one being built in India. So the more of these that we have, they will each detect the same events more than likely, but they'll detect them maybe at slightly different times.
Different angles, perhaps?
Yeah, different angles. And so you will then be able to better pinpoint where in the sky these phenomena happen. Because right now, with the two LIGOs, one is in Washington State, one is in Louisiana. And so they both pretty much detect the same things, and they're just slightly different. One might detect something just slightly before the other one. What's happening is this ripple in space-time is going outward, and it's actually lengthening or contracting
the laser?
The laser, yeah, the pathway for they come at, they're at right angles. So two lasers, if the pathways change in length, you get a detection then where the laser is, the two lasers, the beams are meeting each other.
And I just think that's so fascinating that the length of these detectors actually changes because the gravity wave that's coming through makes them stretch out, just the way space-time stretches around a massive object.
And it's not just the detector is stretching. You and I are stretching too.
We just don't feel it.
Earth is stretching, we just don't feel it. This is just at such a small, tiny, tiny amount. Einstein and others had said, yeah, this is possible to happen, but no, we'll never be able to detect this thing. But it took a whole lot of people doing a whole lot of physics for a really long time.
And a whole lot of computer power.
A whole lot of computer power, a whole lot of amazing engineering to make these finally happen.
I think one of the most fascinating things I find about astronomy is the amount of engineering that goes into it, and just how complicated these things are, and how precise, like as you've mentioned with LIGO, these detectors, the amount of difference is so infinitesimal that you would think it's unmeasurable, which is, I'm sure, why Einstein thought we'd never be able to detect
It's a fraction of the size of an atom, just insanely small. I love to say, who thought that was a good idea? Who
thought we could get there?
Who thought we could actually do this? And someone's like, no, we can do this. We just got to work on it. And that's what I love about just science in general.
And now with the LIGO, not to go too far into that, but there are, as you say, there are more detectors that are coming online. And the first gravity wave detection was big news when it happened, whenever it was, a couple of years ago. But now they're kind of routine. We see them all the time, or relatively speaking. We see a lot of them, right? So it wasn't just a mistake. It wasn't just a lucky fluke.
Right.
These things actually work, and we can actually do this now.
Yep.
And I get such a kick out of the fact that scientists or astronomers refer to it as now having ears.
Yeah, because it's some of these phenomena that are happening, collisions of black holes, they don't give off light that our other kinds of telescopes can detect, X-ray telescopes, visible light telescopes, whatever. That can't happen. This is the only way we have of being able to study these phenomena. And then the other thing that LIGO has proved itself useful for is one of the most recent detections, which was 2 neutron stars. So to explain, stars larger than our sun, they will explode, called a supernova. So our sun will never do this, so don't worry.
Not enough mass
Not
there.
enough mass. So our sun will not explode, but these big stars do. If there's enough stuff left over, the material kind of crunches down until it's essentially a ball of neutrons. The protons and electrons, think back to your chemistry class, everybody. The protons and electrons essentially just kind of squish together, and so now you've got a ball of neutrons, several miles wide, and
incredibly
maybe about
dense.
the size of a city. What's that?
Incredibly dense.
Incredibly dense. And this object, if there are 2 of them, and they are rotating around each other and they collide, that does give off other types of light and gravitational waves.
So you can look at them both visibly.
Yes, and that was the most recent amazing discovery from LIGO. LIGO detected it, and some other telescopes were able to detect it. Something like, there were like 3,000 astronomers on the planet were involved in these various detections with these various observatories and telescopes and LIGO and everything. It was
So now
just astonishing.
it's almost like going from a 2D picture to a 3D picture, because
Yeah.
you've got these different ways of measuring this.
Yeah,
now.
and that was another thing, was this thing we were able to pinpoint where it came from. So with the 2 current LIGO detectors, we can only get kind of a strip of the sky where we think this phenomenon was, where it happened. As more of them come online, we'll be able to pinpoint that down a little bit more. But thanks to these other telescopes, we go, oh, well, this happened in this galaxy, this many 100 million light years away. And it's really cool.
So since you've brought up the word telescope,
Yes.
we have something here that
Yes.
looks suspiciously like a telescope.
It is, yes.
Can you tell us about this?
Sure. This is something that showed up in my office about an hour before I left today. So this is brand new, but it looks really old. It is a replica of Isaac Newton's telescope. So to explain that, Galileo did not invent the telescope. He's often colloquially credited with it, but he didn't actually invent it. For as momentous as an engineering feat that was, we actually don't know who invented the telescope. It was possibly an eyeglass maker.
Probably a woman, right?
I would hope. But it was probably an eyeglass maker, because it doesn't seem too far of a leap to go from 2 glass lenses side by side to 2 glass lenses in a line. And so somebody invented it. In 1608, no one had a telescope. In 1609, everybody had a telescope. But they were used primarily as military tools, because you could see who's coming from farther away, and get more prep time for someone who might be invading your city. And so Galileo improved upon this tool, and he also pointed it up at the sky, and he also was not the first person to point the telescope up at the sky, but he wrote about it, he published, he talked to a lot of people, so we now know Galileo quite well. So that was about 1610 when his book, The Starry Messenger, came out. 1668, Isaac Newton invented the first operational, what's called a reflecting telescope. So if you look inside this tube, there is a mirror in there. It's down at this end.
I can see it,
Yeah,
yes.
so I'm going to attempt to turn it.
See if the camera can pick that up.
Pick it up. There we go.
Yeah, like we can.
So you can see it kind of shining a little bit.
Yeah.
So there's a mirror down at the back end of the telescope, so I'll turn it sideways. So down at this end. And so the light comes in through the tube at the front. There's a curved mirror here at the back. The light goes back up essentially as a cone to a flat mirror that's right about here, and then the light gets shot out through the eyepiece right here. So you put your eye here. And so there were other people who, there's another person at least who came up with this idea for a telescope, but it wasn't a working version. But Isaac Newton made the first actual working version of this kind of telescope. So this is what it looked like. This is how big it was, or how small it was, I should say. The mirror was only about that big across, so about 2.7 inches across.
But it was powerful enough for him to see things that others had never seen before.
And the thing that I noticed immediately was when you look at a replica of Galileo's telescope that we have at Adler, we've got a working replica that people look through. We have our telescope volunteers that take this replica out as often as they can, and we pointed at something, and it is really difficult to look through this thing because if you're looking up at something in the sky, there's no motor or anything to keep you pointed at what you want to look at.
Yes.
The view is really small, and so it's hard to look through this telescope. This one, you can see how nicely it moves on that ball, that wooden ball that's there at the bottom. And so I can kind of point it at something and then, it isn't motorized, I can't track it, but it's easier to move this than and actually point it at something and keep it pointed at something than it is for me to use my Galileo replica telescope.
Which you really had to hold by hand.
You had to hold by hand or put it on a tripod of some sort.
Yeah, and move it around.
Yeah, yeah, and so you also notice how short this is. My Galileo replica, the lens is about that big. It's about an inch or so across, a little bit more than an inch. This is 2.7 inches, but my Galileo replica telescope is about that long. This telescope, because you folded the light path on itself, you can make it shorter.
Turn it back.
Yep.
Right.
And so at the time it was hard to make glass lenses, hard to make mirrors, but rapidly it became easier to make mirrors than it was to make lenses. If you think about it, you only have to figure one side of a mirror, but two sides of a lens. And so by the end of the 1700s, the largest lens telescope, refractor, was maybe about that big. The largest reflector by the end of the 1700s was, I believe, about 50 inches across, something like that. Big, really, really big compared to glass lenses.
Of course, today we have multifaceted mirrors.
Absolutely, yeah. Telescopes that it isn't just one mirror, it's a system of many mirrors, and you can make your telescopes enormous. However, the Hubble telescope still rules them all.
Because it doesn't have to filter the atmosphere.
Exactly. It's up above all that murky air. So, so this replica telescope, which, again, same size, same everything, modern eyepiece, of course, modern optics.
Yes.
But we intend to take this out and have folks take a look at it and compare it to the Galileo replica and then a modern telescope.
Well, speaking of things in outer space, you've brought some replicas, so actually some actual items
real
from outer
stuff,
space.
yes.
So let's start with this one up front.
Yes. So this is a piece of a rock that, it was a larger piece originally. This rock was found in Northwest Africa. And if I turn it over, you can see it kind of looks sort of reddish a bit, maybe, I don't know if the color is coming through real well, but if I turn it over, then
you can see it looks very charred.
Looks very dark on the outside, yeah. So that is a meteorite, and this rock specifically came from Mars.
So I need to stop you there because it brings up so many questions.
Yep.
I'll get to how we know it's from Mars later, but first of all, assuming that we know all this and all this is true, how did it get here? It started on Mars.
Yeah.
I don't think anyone picked it up and threw it out into
No,
space.
not yet.
So not yet, at any rate. No one we know of. So how did it?
Elon Musk's Tesla is not to Mars
it's
yet.
Not there
so
yet.
Nope.
So how did it leave Mars in the first place to get here?
Yep. So something from space, big, smashed into Mars, and we think we have a pretty good idea, maybe of, I should say, there's a scientist who thinks he has a pretty good idea where on Mars that rocks like this came from. Anyway, made a big crater, but some of the rocks were going so fast that they escaped Mars's atmosphere, they escaped Mars's gravity, traveled through space, came in through the Earth's atmosphere, and this is where we get to do this is where we have an interactive portion of the presentation. So put your hands together, all right? Everybody at home, put your hands together. Rub them real hard. What do you feel?
Heat.
Heat, caused by?
Friction.
Friction. So if you can rub your hands together at 25,000 miles an hour.
Yeah, I'll try that maybe after the show.
129,000 miles an hour, whatever, give or take. So basically, you've got these rocks going really fast, and so they come through the Earth's atmosphere. The outsides of them heat up, but they heat up due to friction with the air. But they heat up so much that the air will glow. So when you're seeing that quick little streak of light in the sky, shooting star we call it, meteor,
That's actually the air. It's
that
not
is
the meteor
the air
itself.
glowing, right? That is the glowing hot air. The thing itself, those quick little streaks, probably only about the size of a grain of sand. But sometimes these things are a little bigger. Case in point, that meteor that exploded over Michigan a month or so ago.
Or the one in Russia.
And the one, the Chelyabinsk meteorite in Russia. So they're going fast enough. They're going through the air. The outside of them will char. The inside will still be cold, and it'll still be, basically this thing's been traveling through space, and space is cold. And so then it will possibly, if it survives, it'll hit the ground. So this thing, that charred remnant, so this side of it will tell us where it's from.
I mean, looking at the inside,
Yep, looking at the inside. This side of it will tell us how it got here. And there's a little bit of sand from the desert embedded in it, so it'll tell us where it ended up, where it landed.
So how do you know it's from Mars?
Great question. So we have quite a few Martian meteorites on Earth now. We're finding more and more. And a lot of times there are air bubbles in these rocks that are trapped air. So it's a sample of the air, at least the gases that were embedded in these rocks originally. And you can test things like noble gases. All right, everybody, think back to chemistry class.
That's pretty far in your rearview mirror for
people like
me.
It's all right. Think that periodic table, that chart of boxes that was up on the wall.
I can picture it.
Lots of rows, lots of columns. Right-hand side, noble gases. Helium, argon, neon, krypton. They don't react much with anything, and so they're just going to kind of sit there. If you test the abundance of those noble gases and you compare it to, say, Earth's atmosphere or rocks here on Earth, compare it to Mars, they match Mars.
Now, who was the first person to figure that out, and how did they? I mean, someone found a rock at some point and said, gee, I bet this is from Mars.
I bet they didn't. I don't know who the first person was, but whoever it was a smart person to say, I don't know where this is from. It is possibly from someplace out in space. I'm going to test it.
But it doesn't match what it should match if it originated here.
Correct, correct. And then you start looking around, and thanks to the rovers and other spacecraft that we've had that have gone to Mars,
now, we know much more about the atmosphere, the
correct. Yeah.
chemical composition of the soil and the rocks.
Yep, yep. And then thanks to the rovers and the spacecraft that are studying the surface of Mars, you can get a sense of which rocks are where, what kinds of rocks they are, and really start to drill down and go, oh, sorry, pun not intended, sorry. And really get a sense of what kinds of rocks they are, compare them directly to the rocks that we get here.
So one other thing, because we're almost out of time, I want to point to that slice of, tell us what that is?
Yep, that's a piece of the moon.
And was that retrieved from the moon?
Nope.
From one of the moon missions?
Nope. So this is a lunar meteorite slice. So this, the rock did not start off that thin. And it looks suspiciously like Indiana.
Yes.
And so this is a slice of a meteorite because sometimes meteorites are more valuable in pieces than they are as one big chunk.
Well, with that, believe it or not, we're already out of time. And I can't believe it myself.
My goodness.
However, as long as I've been doing this show, this is the fastest it's ever gone. So we're just going to have to get you back at some future time.
Absolutely. And I just encourage people, come to the Adler,
Come to the Adler
and
Planetarium.
touch this stuff. Yeah, come on down.
So, Michelle, thank you so much for being here. It's been a pleasure. I feel much more educated now.
Thank you so much. I had fun.
And thank you for joining us once again on Public Perspective. I'm your host, Kevin McDermott. You can find us every Saturday night at 8 on Comcast Channel 19 and see us on the web at publicperspective.tv. So until next time, thank you and good night.